Welcome to the first and only class on curve sketching. This is all about, as it says, curves, and eventually we're going to be able to sketch curves. And by curves, I mean sketch something like this without using a graphing calculator, just by using its main points. And the three main things we're going to be looking for are x-intercepts, other things called critical values or critical points, and also inflection points, which we'll get to later. But basically what this relates to is the function as it is, the first derivative of the function, and then the second derivative of the function. But we'll get to that as we get to it, okay? And at the end of the day, you're gonna have one multiple choice like this on your final, but you don't know what it's gonna be. And so we need to just fully cover everything because it could be anything from this, all right? So I'll get started, and if I'm going too fast, you just ask your questions as you need to, okay? So I already put a few notes here. It says we can use our knowledge of limits and derivatives to help us to sketch curves, no matter what the curves look like. And the main things we're going to be looking at are the intercepts, like I said, the critical points, which are related to the first derivative, and the increasing and decreasing sections of a function, which are related also to the derivative. The other pieces, vertical asymptotes, horizontal asymptotes, domain and range, different behaviors, those are smaller concepts that I'm not going to spend as much time on. I'm just going to mention them briefly, and things we've already seen before. So for this first example, it's just saying, look at this function. We can say see the function goes down, and then the function comes up from infinity and goes on forever. So what you should notice about this function is that it has an asymptote. It has a vertical asymptote, which we've talked about before, at x equals 3. So the reason that is the case is because this number on bottom, if you look at the original function, if we set x minus 3 equal to 0, we can figure out that x, if it's 3, will make this function explode, which is why we have this x equals 3 value as a vertical asymptote. You should also notice that there's a horizontal asymptote, which is a little less common, but a horizontal asymptote, which is, it will never touch it in the horizontal direction. And what value is that at? Well, we need to look at it. This is our origin here. So really the horizontal asymptote is at y equals 2. So this 2 and this 3 are important. The horizontal asymptote is at y equals 2. You don't need to worry too much about having to answer that question on the test. I just wanted to cover it. But we can look at this function and see that there's two things going on, vertical and horizontal asymptotes. And they're both really easy to find, which we'll find in a second. On the next page, it says intercepts. And intercepts are where you cross either the y or the x-axis. They're also called roots, they're also called zeros, they're also called solutions. But all they mean is the values of x that satisfy the equation f of x equals 0. You might have done this before, you might have not. Hopefully you have. So let me just give you your basic information. X-intercepts occur where y equals 0. So you would look, this could be an x-intercept, this could be an x-intercept, this could be an x-intercept, because when y equals 0, that's what we see. For the y-intercepts, if you had a function, it's where it crosses the y-axis. So that's where x equals 0. And that's when we set x equal to 0. So you'll notice these things. X-intercepts when y equals 0, y-intercepts when x equals 0. This is not new. If you want like a really short way of remembering this, the steps are to set y equal to 0, because that's where the x-intercepts are, and then solve for x. For the y-intercepts, you set x equals 0 and solve for y. So let's go ahead and do the example. Again, normally I would be going back and forth with you more, but these are pretty simple concepts. So once we do the examples, I'll give you some time to ask me a question, and then we can move on again, okay? So find the x and the y-intercepts of this function. So very simply put, if you want the x-intercepts, you set y equal to 0, or set the function equal to 0. That means that we have 0 equals x cubed minus x squared minus 6x. We need to solve that. So I'll just show you how to solve it, and once you see it, if you still have questions, you let me know. I need to factor it first because it's very difficult to solve for a cubic. It's really easy to solve for a quadratic. Take the x outside, leaves x squared, x, and a 6. That's because if I was to multiply back through, I would get this answer again. So it's factoring out the x. What are my factors of this? You should have known that from the last topic. You know, you have an x and an x. What two numbers multiply to make 6? So that could be these two. And add to make -1. Well, it needs to make -6, so it's either 1 times 6, -1 times 6, or 1 times -6. Or it's -2 times 3, or 2 times -3. So which one is it? Well, it has to be, by me looking at this, it's going to have to be these two. It's going to be 2 and 3. If you have a +2 and a -3, you multiply them, you get a -6. If you add them, you get a -1, which is exactly what I'm looking for. Hopefully that's okay so far. Again, let me know if there's any issues. How do we solve this for x? Well, it's actually very simple. My method, I find, is very simple. You have this x piece, you have this x plus 2 piece, you have this x minus 3 piece. If any of those were to make the function 0, it would all go to 0. So what I'm saying is just split them up. Set that piece equal to 0, so that's actually solved as it is. Set this equal to 0, x plus 2 equals 0. What does that give us? We'll bring the 2 to the other side, we get a -2. And if you solve the other piece, x minus 3 equals 0. Again, setting each individual piece to 0, I get x equals 3. So I've got 3 x-intercepts for this function. And if I was to just show you what this looks like, my 3 x-intercepts would be at 0, at -2, and at 3. This would be at -2, and this would be at 3. That's where my function would go through. So maybe it looks something like this. We don't know for sure, but that's about as good as I can say right now. If I want the y-intercepts, what do I need to do? Well, I told you earlier, if I want the y-intercepts, I said above here, we'll make it the same color so you can make the comparison. Set x equal to 0. That one's really easy. So our function is y equals x cubed minus x squared minus 6x. So it's 0 cubed minus 0 squared minus 6 times 0. Well, they all have 0 in them, so they all go to 0. They're all gone. Our y-intercept is at y equals 0. That question's done. So what I know is the function probably looks like, if I was to make a sketch of this, which I'll say is not necessary because I'm just making a note here. I'd have my axes, I'd have an intercept at -2, at 0, and at +3. And I know what cubics look like. They look like this. So it would look like this. That's our function. I'll just put it in a little bubble so that you know it's not actually necessary. This is just for your information. Okay? So our final answer, what are the x-intercepts? Well, I'll make a little table. I'll say, so our intercepts are 0 and 0, -2 and 0, 3 and 0. Or you could even put it in a table of values if it's faster for you or more clear. The x-intercepts, that's where y is 0. We'll have 0, 0, -2 and 0, 3 and 0. Okay. So let me just rearrange this on the page here. While I'm doing that, can you just let me know if you have any questions? This should be review. You should have seen something like this before. Okay. Any questions? Can you all hear me okay? All right, so that's solving for x-intercepts and y-intercepts in the same question. Very straightforward in my opinion. Let's move on to another type of question, vertical asymptotes. So vertical asymptotes are what we saw before. They would look like this. There are these lines that, the function can never touch. It's when you have these graphs that go to infinity at some point. So to make it clear, vertical asymptotes can be found by finding x values that make the denominator 0, find x values that make the denominator 0, and they also can't be canceled. So they're not a whole. Remember, we can, it's not a removable discontinuity. So those of you that are just jumping in, this is page 4 of 18. Just so that you know where we are in the unit 6. Let me show you how easy this is to find. So it says in the case of removable discontinuity, these values represent holes in the graphs, not asymptotes. So let's look at this first example. Describe what happens to the function as x goes to -3. Well, first of all, let's see if there's asymptotes. You just do the same thing we did last unit. Factor everything. So let's factor. The top should be easy to factor. The bottom is already factored. The top, let's see, what makes 12? What makes -12? And the two factors add to make -1. That would be a -4 and a +3. I'm not going to go through that. What I will say is that if you are having trouble, and a lot of you already know this, your calculator can solve these basic factoring problems for you. So I'll just show you, in case you don't know that. On your calculator, you go to mode and equation. You can solve all sorts of equations. And I just want to solve the top. I want to set this top piece to 0. So I need to do my third mode, which is quadratic mode, set to 0. So choose mode 3. What's your a value? The value in front of the x squared, it's 1. Press enter. The next value is -1. That's the one in front of the x. Press enter. And then put in a -12. And press enter. What that'll give you, and if we press enter here again, the first value is a 4. You just change that sign, it'll give -4. Because of course, if x equals 4, then x minus 4 equals 0. So you'll notice that this 4 relates to the 4 over here, right? We've got this 4, it's actually x minus 4, they're related. If we press the enter again, we'll see that it's actually +3. So those are our two roots. You can do that anytime you want to solve or factor your questions, all right? Hopefully you've seen that before. It's very useful. So my whole point is, in this question, the top and bottom cancel, which means our function is x equals -4. It has a hole at x equals -3, which we've seen before. That's because it canceled. And no asymptote. I'm actually not going to go any further on this because I'm not planning on asking a question like this very much. But as x goes to -3, it just, as it approaches -3, it approaches the value of 7. But I want to talk about asymptotes here. So once again, removable discontinuities are also called holes, and they are canceled. Vertical asymptotes occur when there's a non-removable discontinuity. So we're going to have the same question, but we can't delete the bottom. So this is more what I'm looking for here. If you need me to go back, let me know. So the function is 1 minus x minus 2 all squared. So it says describe what happens as x goes to -2. Well, if we just look at this based on limits, we can see that the right side goes to infinity, and the left side goes to infinity. So really what we're talking about is it goes to infinity when x goes to 2. But how do I find vertical asymptotes? That's really, I'm going to ask the question, any vertical asymptotes? Set the denominator, or the bottom, to 0. Let's do that. The bottom is x minus 2 all squared. I'm going to set it to 0. That is the same, you know, I can just square root both sides, which is the same thing as just deleting the root, or sorry, the power. Same thing here, the square root of 0 is, of course, itself. So what am I getting here? What's my x value? I'll leave that last little step to you. What's our x value? Anybody alive? 2. So the whole point here is if I've set the bottom to 0, all that means is I have a vertical asymptote when x equals 2. And that should not be a surprise because I look at the graph and there's a vertical asymptote there. That's all it's asking about. So what happens to the function as x goes to 2? So the function goes to infinity as x goes to 2. We don't need to break it into anything more complicated than that. You just need to look and see, are there vertical asymptotes? If there are, then you just tell me where it is. Okay? And in this case, we can see the graph. It goes to infinity as we reach that asymptote. But again, not really the whole point of this unit. So I just wanted to cover it and move on. All good? On a scale of 1 to 10, how okay is it if I can move on from this? Because I want to get to the more interesting stuff. And honestly, easier stuff in a lot of ways. Ooh, a 10. Nice. 8, 10. Woo! It's a good day. Okay. Well, horizontal asymptotes. This one is going to go by very fast. I'm just going to do a very quick one. To get horizontal asymptotes, check if the function values y have a limit as x goes to infinity. If the limit exists, then there's a horizontal asymptote. So this is our basic idea. They can be found by getting the limit. Very simple, as x goes to infinity, okay? The limit as x goes to infinity of this function. Well, the function is 1 over x minus 2 all squared. How do I get the limit of this? Well, just consider, do direct substitution. Infinity minus 2 all squared is still just infinity. This is huge. It's just the biggest number you could possibly imagine. So if you square it or subtract by 2, it doesn't matter. It's still 1 over infinity. And what do we get when we go 1 over infinity? It gives 0. So this is a review of limits. I'm not going to review that again. We already did this in the last unit. But I will just write the final answer. As x approaches infinity, the function approaches 0. And the reason I did that is to say there is a horizontal asymptote, which I'll just call HA, at y equals 0. So that's the whole point of the question. If you get the limit as x approaches 0, this will give you a value. It could be 1, it could be 2, it could be anything. In this case, 0. And that means that that's your your horizontal asymptote. And that's all there is to it. It's the only example of it I'm going to do. I can do another one. Do you want me to do one more? Maybe I should do one more, just so you can get comfortable with this. Let me give you another example. Find horizontal asymptote of function is x squared plus 2x squared plus x minus 1 over x squared minus 5x. Anyone remember how to get the limit of that as it goes to infinity? Let me refresh your memory. You just had a test on this stuff. So as a shorthand, horizontal asymptote, you need to get the limit as x approaches infinity. You can also do negative infinity, but infinity usually works just as well for now. The limit as x approaches infinity of our function. Some of you got this right on the assignment and test, some of you didn't. What you need to do, divide everything by which value? Hopefully you haven't forgotten already. The highest power in the denominator, which is x squared. Divide everything by x squared, and now we can do it. That's what we do when the limit goes to infinity. So that gives 2. This would give, let's see, 1 over x. This would give 1 over x squared. This would give 1. This would give 5 over x squared. And if you're good with your limits, you know that as it goes to infinity, it becomes this massive number, which is just going to delete this, going to delete this, it's going to delete this. And what it leaves us with is 2 over 1, or 2. So this topic actually is just an application of what we did in our last unit. And the reason it's an application is because I can now say there's a horizontal asymptote at 2. And what at 2? It's y equals 2. The reason it's y equals 2 is because I'm talking about a function, and that's the same as saying y. So really it's solving for that y value. Normally I would go ahead and graph all this stuff, but again, this is just a really, really short topic. We've actually done it before. To give you your cheat sheet, if it asks for horizontal asymptote, get the limit as x approaches infinity. End of story. If you did your studies properly in the last unit, that's not a new topic. You should already know how to get the limit as it goes to infinity. So it should be easy. I'm hoping it'll be easy for you. If not, you can go ahead and review it again later. Okay, I'm going to keep going unless you stop me. Just at any point in the chat, say, "Sir, stop," and then I'll wait, and we can just talk about it. Okay, let's move on. Domain and range, I'm going to give you a favor here, and I'm going to skip it because we've covered it earlier, and it's not crucial to this particular unit. So I'm going to skip it. Homework is the next section because I've done all this. Vertical asymptotes, I'll just give you a reminder. Set bottom to 0 and solve it. For horizontal asymptotes, find the limit as x approaches infinity, or negative infinity, as you like. 3, find the x and y intercepts. If you want the x-intercepts, set y equals to 0 and solve for x. If you want the y-intercepts, set x equal to 0, solve for y. Because you're looking for a y-intercept. Sorry, one second. Find the y-intercept, set y equals 0, solve for x. Yeah, those are the x values that it would cross the x-axis. And for the other case, it would be the y-axis. So solve for the y values. For the next practice, again, I'm just giving you an idea of how to approach these. Find all asymptotes. Well, I just told you how to do that. All asymptotes, there's only vertical asymptotes and horizontal asymptotes. So you just find those. And then the last step here, I'll just say skip the domain and range. The reason I'm skipping through this is because they're the same type as we just did. I'm going to post the full solutions. I'll post my workings for this so you don't actually miss anything. But you've already got the basic ideas. I want to move on to the sort of more interesting stuff. What are the restricted values of the domain? I'm going to get you to skip this. Are there any, actually, we can do this one. Restricted values, just set the bottom to 0. We've done this before in a previous unit, but as a reminder, we're not allowed to have -3 because we would divide by 0. Sorry, I'm giving you the speed class today because we have so much to cover, but again, if you need me to slow down, I'm still here to slow down for you, no big deal. What are the x-intercepts? What are the y-intercepts? We've already done those. Are there any vertical asymptotes? We did that. Are there any horizontal asymptotes? We did that. So the basic ideas are covered. Okay, I'm now going to move on to what's called critical points and critical values. And the critical points and critical values are all based on the idea of a maximum and minimum points. They're also called critical points. And the big idea here, maximums and minimums occur when f prime equals 0. So let me try to compare this. Let me slow down and just repeat what I said here. The maximum and minimum point of a graph are the highest points and the lowest points. And when you look at them, they actually have a slope of 0. So when it says here that f prime equals 0, it also means that slope equals 0 because slope is the derivative. Let me try to make it more clear to you. If you go to this QR code, or there's a link in my notes here, once you see the notes, I'm going to bring up this. And just allow me to set this up for you. First of all, I want to label something here. If you look at this graph, we're looking at this graph here. You don't need to worry about what that dot is. We can easily see where the minimum values and the maximum values are. This value down here is a minimum. We don't care what it is right now. This is a minimum. It means the smallest point. And this up here is a maximum. Highest point is our maximum, just like the top of a sine curve or a cosine curve. The minimum point is the bottoms, which are the bottom points of the curve, of course. The interesting thing is, and let's look over here, I want to make a note about the first derivative. Take a look at this box. It says our derivative is negative. Okay, let me just show you. Follow this little dot here. On this point here, the slope, it says it's 22, or in other words, it's positive. Why is the slope positive on that point? It's because the tangent, which is the derivative, is positive. So look at the slope. I'm going to give you a little exercise here. I'm going to ask you to tell me, prepare the word stop in the chat. And I want you to type stop when I get to a point where slope is 0. Okay? Right now the slope is positive. I'm going to move this dot. You tell me to stop when I get to a point where slope is 0. I'm not seeing any stops. So I'm going to keep going. I'm into a negative section now. Negative, negative, negative. I'm in a really steep negative. Really steep negative. Have I hit 0 yet? Is my slope going close to 0? Is it flat yet? Well, I'm going to go ahead and just tell you that I think I should stop here. And Juma caught it yet. So over here, look at my slope on the left side. My slope is 0. And where am I? I'm at a minimum. Because the slope is flat, it had to go from negative, it had to stop and become 0, and then go back up. It's like if you threw a ball in the air. Look over here. On the left side, it has to go up, up, up. It's slowing down, slowing down, slowing down, slowing down, slowing down. Over here, it's actually 0 because it has to stop, and then it comes back down. So the whole point of this is for me to tell you that when the slope is 0, it is a max or a minimum, usually. Generally speaking, in this course, that's what you will get. And the reason for that is because the slope is 0. The slope is the tangent. The derivative is the slope. All these ideas are connected. So long story short, what we're going to do is we're going to get the derivative of our functions and then find those values where slope is 0. It's actually really, really, really simple to do. Let me just take one more look. See this tangent line? Negative, 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 negative. It's getting less negative, less negative, less negative. Oh, it turned into 0. Now it's positive, 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 positive. Oh, it turned into 0. Negative, changed sign, went positive again. So we're going to be talking about that a lot. And I hope that made some sense to you. Let's connect it back to our notes. Maximums and minimums occur when the derivative is 0. So for example, if we had a function like this, at this point and that point, the slope is 0. Slope is 0. We're going to follow a very, very clear, easy process to solve these questions. 3 steps. Find the derivative, find where the derivative becomes 0, and then substitute those back in to get y values. Let's just go ahead and do this. I'll keep the steps there. Identify the critical points, which generally mean the maximum and minimum points of the function f of x equals x cubed minus 3x squared. Okay, let's do it. What's the first derivative? That should be the easiest thing ever. You can get a free mark here if you have any idea how to do the power rule. It's 3x squared minus 6x. Nice and easy, right? We've got the first derivative of that function, and we've now completed the first step of finding critical points. Now we just need to set it to 0. That's very easy. Set this to 0. Okay, let's try to solve it. Let's do ourselves a favor here. Do we have any common factors? What's a common factor between this and this? I can see that I could probably pull out a 3, because 3 is common to both. And I think I could pull out an x. 3x, Nasser says. 3x. If I take 3x out of the first one, I'm left with an x. If I take 6x divided by 3x, I'm left with 2. You can quickly check your work and say, if you multiply that, yes, I get this. You multiply this, yes, you get that. Okay. 1 second, I just need to turn on the AC. It's very hot in this room. Sorry about that. So let's solve this. We can easily solve this for x just the same way as I solved it before. On the left side, if I set 3x equal to 0, x must be 0. If I set the right side, x minus 2 equals 0, x must be what? Bring the 2 to the other side, x must be 2. X must be 2. All right, these are my critical points. If I had to set these in a table of values, because it says I want the critical points, which means x and y. By the way, in this step here, find out x where the derivative is 0 or where it's undefined. These values represent the critical values. I've got them. They're these. Okay? When x equals 0 and x equals 2, what's my y value? If I put it back into the original function, setting x to 0 here, I get 0 back. Let me show you. F when x is 0 is 0 cubed minus 3 times 0 squared. That's definitely 0. That's this one here. I'll keep it there, actually. F at my critical value of 2. Well, that's 2 cubed minus 3 times 2 squared. That gives me what? 8 minus 12, so negative 4. And long story short, it says, identify the critical points of the function. Let's identify them. We know our critical points are at 0, 0, and 2, negative 4. All right, before I go any further, did I lose you at any point? First derivative. Set it to 0. Solve for x. Why do I solve for x equals 0? Why do I solve when the function 0? It's because that's when the slope is 0. These values of x make the function 0, make the slope 0. I'm going to do one thing over here on the side. The notes do it a little bit later, but I'll just read ahead and then come back into this example, okay? It says for increasing and decreasing functions. It said in the graph at the beginning, we saw that leading up to the minimum of the graph was decreasing. Well, okay, 1 second. I'll explain this in a different way because I don't like how the book is doing it. If the function is increasing, it means that the slope is greater than 0. If the function is decreasing, it means that the slope is less than 0. Let me show you exactly what this looks like. I'm going to graph, well, I'll bring up this again, actually. Look at this. In this whole section here, the function is decreasing. Let me draw on it. Between these points here, everything in this region, slope is less than 0. It hits the minimum, it goes back, now slope is positive. So in other words, in this point, the slope is negative. In this point, the slope is positive. In this point, the slope is negative. At any point afterwards, the slope is positive. Okay, these are our big ideas. What's another word for slope less than 1? Well, negative. So that means the slope less than 0. Slope greater than 0. Slope less than 0. Slope greater than 0. I'm giving you all sorts of terminology. They all mean the same thing. Just want to make sure it's covered. You can always watch this video as many times as you want. I'll clarify this one more time, just so it's crystal clear. We have the function is increasing if the slope is positive. And we have decreasing if the slope is negative. So I'm going to go back in time a little bit and go back to this example. I just want to show you this one note here. First derivative test. To determine if a critical point is a maximum or a minimum, we need to do the first derivative test. We need to see if it changes sign from decreasing to increasing and from increasing to decreasing. Let's go back and I'll show you this very clearly. Just pretend I didn't say that. Just follow me if you're lost. I'll help you get back on track. For this question, example 1, I had this function. I got the first derivative, and it gave me 2 critical points, these 2. I'm going to take those and make a little number line with 0 and 2 on it. 0 and 2. And what I want to think about is what is the sign of the first derivative here. So first things first. I want to figure out if it's increasing or decreasing. I'm just going to do that with a plus or a minus. So if I put in the function, if I put in the x value x equals 0 into this is the first derivative, what am I going to get? Well, 0 and 2 both give 0. What if I put in, let's just do a test value. Anything in between here, what function is it going to give? What sign is it going to give? So we want 3x and x minus 2. Put the number 1 into that. What's the sign, positive or negative? Well, 3 times 1 and 1 minus 2. This gives us a positive. This gives us a negative. What's a positive times a negative? It's a negative. So I have a negative region in between these 2 critical values. I'm just testing any point between 0 and 2. You can try the number 1.5. It'll give you a negative number. Try the number 0.5. It'll give you a negative. We're going to do this many times today. Let me try to see if you can follow me here. Any number greater than 2. What's the sign going to be, positive or negative? Well, look at this one here. Put in a 3, or put in a 4, or put in a 6, or put in a 10. Let me do it on a calculator so you can see what I'm doing. Let me put my mode back. Just give me 2 seconds here. Oops. So let me be clear. I want to check and see after 2, what's the sign of the first derivative? So put in any number bigger than 2. So for example, I've got 3 times something, you can put in 10. So 3 times 10, and then I need to put that 10 in here, 10 minus 2. What does it give me? 240. I don't care what the number is. What I care about is that this is a positive. All right? It's a positive, so I put a positive here. Anything above 2 will give me a positive number. All right? So that's the big idea here. I need to close this because my computer is being crazy. That'll give me a positive. And finally, anything below 0. What's a number less than 0? Give me any number. Just so I know you're alive out there. What's a number less than 0? -1. Okay, let's try 3 times -1. Again, I'm looking at this piece. That's my first derivative. And I'm going to put in -1 for x, take away 2. What sign is that? That's also a positive. So again, I don't care what the number is. I care that it's positive. And I'm going to put the positive less than 0. So anything below 0, the slope is going to be positive. And if I graph this, which I will in a second, I'll make the connections again for you. But for now, that should be enough. So long story short, what was the whole point, right? What was the whole point of me doing this? Well, it's to tell you if it's a maximum or a minimum. If you have a positive slope, your function looks like this. If you have a negative slope, it looks like this. If you have a positive slope, it looks like this. So imagine from a positive to a negative, positive slope to a negative, that's a maximum. And a negative slope to a positive, that's a minimum. So long story short, if it goes plus to minus, it's a maximum. If it goes negative to plus, it's a minimum. Okay, I know there's lots of ideas throwing around here, but I want to get them all on the table, and then we'll start doing practice and you can start seeing the patterns. All right, I know it's very much to take in the first time around, but you'll see there's a pattern and a method to the way that I'm doing this. Okay, so let me recap what I did here, because what I actually did here, very sneakily, this is called the first derivative test, which means I test my values to see if they're a maximum or a minimum. So what I did, I needed to identify the critical points of the function. That means get the first derivative, solve for function equals 0. Whatever those x values are, they're either a maximum or a minimum. I just made this number line to tell me if they're a maximum or a minimum because I can check the slopes. If the slope goes from positive to negative, of course it must go positive to negative, it must be a maximum. If it goes from negative to positive, it must be a minimum. So these two things here, or more importantly, these 2 points here, this maximum and minimum, I can label them. The point 0, 0 must be a maximum, the point 2, 4 must be a minimum. And after all of that, let me graph it, and we can see that we're right, okay? Let me graph it for you. I'll bring up Desmos as I normally do. And this can be something you can do too. You can always check your work on Desmos. And for this unit, probably more than any other, I'd recommend that you graph the function, because you can be sure that you're right. So Desmos here. What do we got? Identify the critical points. So put in the original function. Let's see what it looks like. Let's see if we're right. Minus 3x squared. Okay, looking good. Let's see, what did I say? I said that our point x equals 0 was a maximum. This is the point x equals 0. It is definitely a maximum. I didn't need to see the graph to know that. The point x equals 2, I said was a minimum. X equals 2 is definitely a minimum. So just by checking it with the first derivative test, which I will review, we can see that it is actually a minimum value and a maximum for the first one. Okay. Did I lose you? Can you just give me an idea of 1 to 10 how confident we are here? I will do more examples. I just want to get a feel for how we're doing on a scale of 1 to 10. There's 7. 7 is probably what I expect. I expected more 5 or 6. Anyone else? I've got a reply from Nasser. It's okay to be scared. It's okay to be scared. So let's do a little example. Oh, there's a little note at the top here. Just kind of a special case. If the sign does not change, it's neither a maximum or a minimum point. So let's consider this function. There's a couple questions here. This is this cubic function. It goes up, down, up. just by looking at this, we can say a few things. Even before I write anything else, I know that B is clearly a maximum. I know that D is clearly a minimum. I know that C is what seems to be a Y and an X intercept. And then there's something weird going on in A and E. Let's answer these questions. Hopefully this isn't too small for you. Let's answer these questions, and let's remember the whole time that slope is f prime. Remember, the derivative of a function is the slope of the tangent line. So let's answer our questions. At B, we have a, okay, at B, we have a what? I think it's trying to ask if it's a maximum or minimum. So at B, we have a maximum. Let's do the next one. At D, we have a what? We have a minimum. And you don't need to write in the chat. You can. I'd love it if you did. But if it's faster for you just to think about it yourself and follow along, that's cool too. From A to B. So from A to B, this region here. So it's saying as the graph goes from A to B, I'll use a better color, from A to B here, it is, well, the slope is positive. We say it's increasing. Okay, the slope is positive. That means that the slope is greater than 0. From B to D, that's this region here. What can we say about the slope? The slope is down, going downhill, which means it's decreasing. The function's getting smaller, it's going down. That's what decreasing means. And if you want another note, that means the slope is negative or less than 0. In the previous case, the slope was positive. This case is negative. Okay, from D to E, the graph is increasing or decreasing. From D to E, from this point to this point, it's going up, so it's increasing. All right, at A, the slope is, all right, the slope is positive or negative. At A, the slope is positive. The slope, again, first derivative, greater than 0, also known as positive. At B, the slope is what? Ooh, what's the slope at B here? What's the slope if we made a tangent line? 0, Abdullah caught that one. It's 0. It's flat. If we draw a tangent line, it will be perfectly flat at B. So the slope is 0. I'll just draw a little line. The slope is 0. At C, the slope is, what is it? This is one that throws students off sometimes. They say weird answers. Okay, Ahmed says it's negative. I agree it's negative. It's going down like this. It's not 0. 0 would mean flat. If you rolled a ball on this, it would go downhill. So it's definitely negative slope. At D, the slope is, once again, 0 for the same reason. And at E, slope is positive. So hopefully you're making some sense out of this. So this is the same thing that I covered in the other illustration earlier. Let me just show you. In this thing, let me see if I get some more interest. So for example, at this point, the slope is clearly positive. At a maximum, the slope is 0. Afterwards, the slope is negative. The slope is slightly positive, maybe there. Negative again, positive again. I hope that you can make these connections. Let's do some more examples. All right. Identify the critical values of the function, and I've changed the function. Please make sure that you also change the function. And then determine where the graph is increasing or decreasing. So critical values, and then tell me if it's increasing or decreasing. Let's do this once more. Let's do our recipe. So I'm going to set up a table of values. I'll keep that on the side. I'll use it later if I need it. My first derivative of my function in red here is 3x squared plus 6x minus 9. I know I'm going to set that to 0 and solve for x. So set it to 0. Factor it if you can. I'm going to take a 3 outside. And I'm also going to go one step further and factor that. You should be able to factor that easily. And it should give you, let me see, positive 3, negative 1. All right, positive 3 and negative 1. So I have two things going on here. I need to set this equal to 0, set this equal to 0. What are my x values? You just change the sign. Very, very straightforward. You set them both equal to 0. One of them will give what? Negative 3. And the next one will give positive 1. Those are my critical values. All right? They come from setting each factor to 0 and solving for x. So let's put those on the table. So I've got, let me color code them so you know where they're coming from. These are just some blue numbers I'm making here. I've got a negative 3 and a 1. Now take those x values, put them into this. Let me make that a little less aggressive. Take these x values, put them into my function, and then put them back in as my y value. What do I get? If I put negative 3 in here, so I need the y value as well. I'm going to put negative 3 in. I'm going to cube it. I'm doing this on my calculator. You can do it at the same time. Cube it. Sorry, my calculator was in the wrong mode. Negative 3, cube it, and add 3, negative 3 squared, minus 9 times negative 3 plus 1. What do I get? Anyone get it? I got 28. That's, if you put in the value of negative 3, you get 28. Hopefully someone tried that. If not, you can take me at my word. If I put the number 1 into the original function, it's 1 plus 3 minus 9 plus 1. 1 plus 3 minus 9 plus 1. That gives negative 4. So my critical values are negative 3 and 28, and 1 and negative 4. So I'll say my critical values are negative 3 and 28, and 1 and negative 4. That's my first answer. Now I need to do something called the first derivative test, which I need to check and see what my graph would look like between these values. It'll look a lot like I did before. Set up a number line, put your numbers on it, negative 3 and 1. Remember, these are going to be used to check my first derivative. First derivative. Okay. What's my, let's check after 1. Okay. Just 1 second. Try to fill out this number line, and I'll be back in a second. I got some tech people here. Sorry about that. My dryer's been broken since I moved into this place, and this is the third set of technicians that came. Okay, so just in case you are a bit lost, what I'm trying to do is to say, I'm trying to figure out if it's positive or negative between the critical points. Because if I figure that out, I can then know if it's a maximum or minimum at the critical point. So I'll write out the workings on the side, but normally I do it in my head. I'm going to say any number greater than 1, because anything in that range, I'm going to say what the slope is. So you're saying 1 and 0, Abdullah. I'm not sure what question you're answering here. I'm not looking for example 3. I'm looking for testing these numbers here. So anything greater than 1. So let's just say the function when I put in the value of 2. I'll put in a 2 to the original expression. Sorry, not the original expression. I'm going to put it into the derivative. I can put it here. So let me show you the way that I think about this. Oops. I would say 3 and then I have a 2 plus a 3, and I have a 2 minus a 1. The way that I think about this is, look, I have a positive number. This would give me a positive. This would give me a positive. And so my final answer is a positive. So anything above 1 is going to be positive slope. Let's do another one. Sorry, Abdullah, maybe that's what I said. I'm going to solve any number between -3 and 1. Do you know what the easiest number would be? It would be 0. I can put in, say, the number 0 here. You can do it in your head. 3, and then 0 plus 3, 0 minus 1. What are my signs here? Well, this is positive, this is negative. A positive times a negative gives a negative. Just think about your sign rules. So the middle here, between -3 and 1, is going to be negative. Let's try one more. Any number less than -3. So let's just say -5. That'd be 3, -5 plus 3, -5 minus 1. Note that these are all my x values. I'm just subbing in that purple formula here. What are my signs? Positive. This would be negative. This would be negative. 2 negatives make a positive. So the final answer is positive. So practice that. I hope that I'm not going too fast. This is just the method we're doing. The reason we're doing it is we're checking the slope. And now it's really easy to see if it's a max or a min. Just follow me up here. Before -3, it's a positive. After -3, it's a negative. So it must go from positive to negative. It's a maximum. How do I know it's a maximum? Because that looks like the top of a hill. It's a maximum. If it goes from negative to positive, again, this is a negative region, this is a positive region, it looks like this. What does that look like? It looks like a minimum. So we can say that the critical values, first one is a maximum, the second one is a minimum. There's not a lot of space given for these, I'm not sure why, but this is how we accomplish this. Fish phone. Okay, can I answer any questions on this, or are you okay? Because this is not super easy to figure out the first time around. I want to make sure that it's clear. So Billa says no, Tadek, Rania, no. I just want to get a quick check, just to make sure that you're all actually here. Can you just say at least hi? Because those of you that aren't actually here, I'm just going to clear the room a little bit. So Nasser, anyone else? Rania, are you still here? Noran, are you here? Noran?
I'm here.
Making sure. A lot of students tend to leave it on and run away, so I'm kind of getting tired of it. Okay, so long story short, the critical values, solve the first derivative, set it equal to 0. Solve for the x values. They give you where it's a max or a min, we don't know what, and then we check the slope between them to see if it's a maximum or a minimum. Let me show you what's going around in the background here. I'll graph it like I suggested that you do. My function is x cubed plus 3x squared minus 9x plus 1. Oops. Plus 1. This is my function. It looks a little bit crazy. I made a double x there. Okay, that's my function. What my work said, or what I just did, the whole reason for all the work that I did was to get my critical values. My work told me that I have critical values at -3 and at 1. Well, look at this. I definitely have a maximum or a minimum there. And I have at 1, I have a minimum. My work, my first derivative test, which is the number line, I checked the sign of the first derivative between them. So any number after 1, you can put any number in there. So I put 2 into the derivative, it gave me a positive value. That means it's increasing at that point. If I put a number in between them, it gave me a negative. That means it's decreasing at that point. If you have a decreasing, touching or changing into an increasing, of course, it must be a minimum. Just by definition, if you go from a negative slope to a positive slope, it has to be 0 somewhere. So it's definitely a minimum, which is why I said it was a minimum. So that's a minimum. If you were to check the slope on the left side of 3, it's a positive. If you check the slope on the right side of 3, but before 1, it's a negative. In order to go from a positive slope to a negative slope, it must cross 0 at some point, which means it's a maximum. Okay, this is my big idea. Before 3, it's a positive. After 3, it's a negative. It must be a maximum. After 1, it's a positive, so it must be a minimum. So I know I've drawn all over this now, but watch it again if you need to. This is not overly complicated. Just check the signs. If it goes from plus to minus, it's a maximum. If it goes from minus to plus, it's a minimum. It's easy for me to say it's not complicated, but I truly believe that with a bit of practice, you'll see it's actually not. So I'll do some more examples so you can get more comfortable with this. Find the values of x for the function which is increasing, and those values for which it is decreasing. Identify any maximum or minimum. So it just means find the critical points. All right, let's see if Abdullah was right. First derivative, 3x squared minus 6x. Set it to 0. I think I saw this one before. Looks familiar. We can say that this is x equals 0 and x equals 2. I'm going to put those in a table. They'll give me my critical values, 0 and 2. If I put 0 into this, it gives back 0. If I put 2 into this, what does it give me? 2 cubed minus 3 times 2 squared, negative 4. I definitely did this one before, but it doesn't hurt to see it again. Now I need to see, is it a maximum or a minimum? So do the first derivative test. I'll make a number line. Put your critical values on it, 0 and 2. And then I need to see what the sign of the first derivative is between those values and after those values. So if I put any number in between 0 and 2, what would be the most logical number to choose? It would be 1. So again, put it into this. Put the number 1 in here. That'll give me this value here, the sign of it. If I put 1 into it, what does it give? Positive or negative? It's 3 times 1. I'll write it here. If I put 1 in there, for example, and then 1 minus 2, that gives a positive times a negative. It must be a negative. So I'm going to write down that this is a negative slope. It must look like this in between those values. Anything after 2. So for example, I'll put in the number, I don't know, 5. 5 minus 2. This gives me a plus. This gives me a plus. It must be a plus. So after 2, it has a positive slope. I'll put in one more thing. Anything less than 0. So I don't know, say negative 1. That'll be an easy one. So 3 times negative 1. Negative 1 minus 2. What does that give me? A negative and a negative. They both make a positive. So there's a positive anything less than 0. Now I can label them. Tell me in order, 0 and 2. Do I have a maximum and a minimum, or a minimum and a maximum? What do I have? See if you're catching on so far. This is half the unit done. Over half, actually. So we have a max, min. So Abdullah is saying we have a max and a min. Ahmed Al-Aswad is saying we have max, Al-Sadeg is saying max min, Tarak is saying max to min. Abdullah or Ahmed didn't say anything yet. Or did you? So max and min. Okay, I saw it. I agree because look, positive slope, negative slope must be positive to negative. Negative and positive must be a minimum. So absolutely, we have those things. At 0, 0, it's a maximum. Here is a minimum. Okay, hopefully it's becoming more and more clear as we do this, what's happening. That is called the first derivative test. Let's do one more. I'll make it hopefully crystal clear to you, and then we'll move on. We'll do concavity and we'll be done. Find our maximum minimum points on the graph of the function. Okay, so in other words, find the critical values. Find the critical values, then do the first derivative test. I'm going to set up a table of values so that I can know what my x and y values are. I'll need it later. So the first derivative, y prime, is, again, do your derivative. 8x cubed minus 6x squared minus 6x, and 4 gives 0. This is a tricky one to factor, but just be careful. Oh, I think I changed this. Sorry. I'm going to change it. I want to give a little bit different function because this one worked out really, really badly. I'm sorry to do this, but it'll help you later. 3 over 2x power 4 plus 4x power 3 minus 45x squared minus 4. The original question didn't work out nice at all. It was really bad numbers. So let's do the same thing. Y prime, this gives 3 over 2 times 4 is 6. So 6x cubed plus 12x squared minus 90x. Set it equal to 0. Let's factor the right side. I can take a 6 and an x outside. 6x cubed divided by 6x leaves a x squared. The next one leaves a 2x. And 90 divided by 6 is 15. So 15. We go one step further. 6x. Let's factor this. What two numbers multiply to make a 15 and add to make a positive 2? Negative 15 and positive 2. If you work at this enough, you should get these two values. I'm not going to show you how, but you should be able to factor that. If you have trouble with it, use your Casio. Finally, if those are our numbers, then I can fill in my table. I have x equals 0, I have x equals negative 5, and I have x equals 3. Or in other words, sorry, I ran out of space, but x equals 0, x equals negative 5, and x equals 3. Now, I know that those are my critical points, but I do not yet know if they're minimum or maximum. So I'm going to do my first derivative test. I have 0, I have a positive 3, and I have a negative 5. I just need to check the first derivative. What are my signs going to be? This is a little bit tricky. You just need to pick good values. Between 0 and 3, I should pick a 1. So for example, I'll take this. I'll put a positive 1 into it and check that. So that's a 6 times 1. So 1 plus, that would be a 6. 1 minus 3 would be a, let me make it clear. 1 plus 5, 1 minus 3. Just check the signs. Positive, positive, negative. Overall, it must be negative. The sign between 0 and 3 is a negative. You don't need anything else. You can just get used to this. What if I do this without any extra workings? Anything above 3. So I can have put a 3 into this. It'll give me a positive. This will give me a positive. When I put a 3 into this, it'll give me, oh, 3 is a bad example. I should use something bigger than 3, sorry. Let's put a 10 in. That'll give me a positive here, positive 15 here, positive here. It must be a plus. Between negative 5 and 0, what's a number we can choose? Any number. Let's try negative 1. 6, negative 1, negative 1 plus 5, negative 1 minus 3. Again, we only care about the sign. I'm just choosing any number between 0 and negative 5. And what are my signs going to be? Negative, positive, negative. Two negatives make a positive. It must be positive overall. You see where this is going? What's my sign for anything less than 5? Let's see if we can figure this out. Pick any number. Try negative 10. What's my sign going to be? I'll do it without talking so you can try it. want to see if I messed that one up. Seems weird. Yeah, negative. Are you still with me? If I ever had you to begin with. You see how the first derivative test is working. We just check the signs. If it's not clear, you have all the time in the world really to check it. Well, not all the time in the world. Your exam is on Saturday, but again, it's only going to be one question, and I'll make sure you're fully prepared for it, don't worry. So from negative to positive here, we must have a minimum. This is a minimum. From positive to negative must be a maximum. From negative to positive must be a minimum. If I was to label these over here, I would have a maximum, I would have a minimum, I would have a minimum. Or if I labeled it in my table of values, I would have a maximum, I would have a minimum, and I have a minimum here. Just to complete this story, you would put in the values for y, but it doesn't actually ask for that. So I'm going to leave it blank for now. Let me graph this and we'll compare it one more time just to see that we're on the right page and to make this story clear to you. Especially if you look back on this video later with more understanding, hopefully you can see, I see how this works, that sort of thing. 3 over 2, x power 4, plus 4x cubed, minus 45x squared, minus 4. Woo, baby! What a function. What a function. Let's see if it matches what we said. So we have at x equals 0, we should have a maximum. We do. Between 0 and negative 5 should be a positive slope, and it should be a minimum here at negative 5, which it is. At x equals 3, it should be a minimum. And it is. And our signs for our slope. Let's check this. It says that between negative 5 and 0, it's a positive slope. Between negative 5 and 0, it's definitely a positive slope. It's going up like this. Between 0 and 3, it should be a negative slope. Negative slope. After 3, it should be a positive slope. And before negative 5, it should be a negative slope. So again, these are the things that I'm trying to make clear to you. There's a lot of moving parts, and you'll probably figure it out on your own bit by bit. But when you watch this video again, watch each section and make sure that what I'm telling you makes sense. And eventually it will click and you'll be like, oh, of course, positive to negative means a maximum, and things like that. So just give me a general idea on a scale of 1 to 10. I know I've never asked this question before. How do you feel about this? I'm looking for anything above a 5 or a 6, because you can always rewatch this. 8. Dun, 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 dun. Okay, 7's good for the first class, well, only class, but on the day that you learn something, 7 is good. Anyone else? 9. Root 81. All right, I've got enough replies in the chat. I'll move on. Let's just go through some basic terminology, and then we'll get to the very last topic, which is called concavity. Instead of talking about slope, we're talking about, does it look like it's curving up or curving down? So as you can see in example 4, a graph may have a number of maximum and minimum values. Collectively or together, they're called relative maximum and minimum points. It's also called local extrema. So it says here, if no function values are greater than a particular maximum, the maximum is called the absolute maximum. If no function values are less than a particular minimum, the minimum is called the absolute minimum. So we just need to classify this graph here as local or absolute. So I'll just write out the answers really quickly. We have the points A, B, C, D, and E. They're all maximum and minimums. We just need to know if they're called absolute, which means the most biggest value, or local. And let me just show you this. A, this is definitely the smallest point on the function, okay? So we call it absolute minimum. It is the smallest value of the function. The point B is a maximum, but look, there's lots of values bigger than B. So even though it's a little hump, it's a little maximum, a little tiny maximum. If we just zoomed in only on it, we would see it definitely looks like a maximum, but there are other values bigger. So we call it a relative maximum. It's only a maximum relative to the way that it looks. It's not a maximum overall. Should have said maximum. All right, what about C? What's C going to be? C looks like a little dip in the graph, but it's not the smallest dip in the graph, or it's not the smallest value. So we'd say it's a relative minimum. D, I'll come back to D. E is also a relative minimum because it's small but not the smallest. And then D is the trickiest one. Can someone hazard a guess at what D is going to be here? Is it a absolute maximum or a relative maximum? Is it the biggest function on the graph, or are there values bigger? Abila's thrown out a relative. I'm also going to say it's a relative maximum. And the reason for that is if we look at D, this function actually would go on forever. So it would there are plenty of values that would be bigger than D, even though it looks like a maximum here, which it is, because it's got this shape, there are values bigger. And so we call it a relative maximum, not an absolute maximum. Okay. So let me go through just a few points here. All this practice section is the same sort of thing. This will all be homework. I've given the answers here, which you can write down, 0, 1, half, and 2, if you wanted to check it. For 2, same story. For C, oops, I dropped my pencil. This would be a challenge. I would never expect you to be able to do that. Sorry, I would expect you to be able to do it, but I'll never ask it at this point. And then we move on to concavity. So I have reached a point now where I can tell you a little story about the main pieces of a function. The story might not be exciting, but I hope at least it'll make some sense to you. We have 4 shapes that a curved graph can take. It can look like this, it can look like this, it can look like this, or it can look like this. All right? Let's look at the second derivative. The second derivative means how curved it is. It's also known as the concavity. In physics, you would say it looks like this, or it looks like this. This would be concave down. This would be concave up. Remember the smiley face and the sad face? That's concavity. So if it looks like part of this, so look at the whole top here. This looks like concave up and concave down overall. They're like pieces of a concave down function. If we look at it this way, that's part of it, this is part of it. We say, oops, sorry, I'm getting too excited. We say this is less than 0, or we say that it's negative. Because look, if we continued the curve, it would look concave down. Concave down means negative. Let's see if you're catching on to this. This function here, does it look like a happy face or a sad face? If we were to continue the function, it would look like a sad face. It's less than 0, it's minus. What about the bottom ones? If we looked at just this, what do we have? Is it positive or negative? Not equals. Positive, yeah. You got excited and didn't hit shift. Plus, the other one once again, it looks like part of this curve, so the concave is up or positive. All right, this is how this works. If we looked at the slopes, first derivative, first derivative, first derivative, first derivative, well, if we just looked at the slope of this graph, no matter how we cut it, is all going to be positive. I don't know who drew on my graph, but I love it. The slope of the second part here, no matter where we look at it, the slope is going to be going down. So the slope is negative. For this case, it's negative. For this case, it's positive. And the reason I'm going through this is because it's going to come up later. I just wanted to mention it now. All right, let me make some notes. This is slope positive, concavity down. I'll say concave down. This is slope negative, concave down. It means it's part of a curve that wants to go downward. This is slope negative, concave up. This is slope positive, concave up. And you can use this as like your cheat sheet later. You don't need to memorize all this. It'll be here for you. And by the time you need it later on, for the final, for example, you should already understand it well enough. You probably won't need to use the reference anymore. But for now, I'll have this in the back of your head, okay? And you can come back to it anytime you want. You can even take a picture, save the video, whatever. So in the notes, it says, we say a curve is concave down if the curve opens upward. And concavity is based on the second derivative, okay? That is, if we were to draw a tangent line, it would be below the tangent. In a similar way, it's concave up. If the curve opens upward, it means that it would be, if we were to draw a tangent line, it would be above the function. But that's not so helpful to many students. If it's less than 0, it's concave down. If it's greater than 0, concave up. Okay, big idea, big important reference points. All right, and I just wanted to put that all out there so that when you need to do these questions, it can make some sense later. Just like there is a first derivative test, there's what we call a second derivative test, which tells us if something's a maximum or a minimum. So it says here, we can use concavity to determine if a critical point is a maximum or a minimum. A curve is concave down or concave up under these cases. It says, if the concave is less than 0, it's a maximum. If it's greater than 0, it's a minimum. It's very difficult to understand this stuff until I do an example, but I'm just putting the important pieces out there, and you can refer to it later, okay? The long story short here is test the critical point using the second derivative. If it's less than 0, it'll be concave down. If it's greater than 0, it'll be concave up. That's the twist. Is it curving up or curving down? Final story. Final piece of information in the entire course, well, except for matrices, but in the entire unit, this is the last piece of information you're going to need. An inflection point is where the points at which the curve changes from up to down or down to up. Let's get started, okay? Let me give you the process. It's the same process as the first derivative test. You get the derivative. The son is very upset right now. I don't know if you can hear him. You set it to 0. You solve for x. You check signs on the number line. Positive or negative. Okay, I've set it all up for you. You probably still don't know what I'm doing this for, but it will become clear once we look at the examples. So the first thing I'll do is look back at this and talk about what I didn't talk about before. let's not look at the tangent. Let's look at the second derivative. In this point here, okay, look at this. Sorry, I'm very distracted by my son screaming behind me. He's outside the door. You can't come in. Notice that in this section here, if you look at the number in the box, look in this box, right now it's positive. That's because it's in an area where the concave is up. Over here, look what happened. Still positive. Something's going on though. There was a minimum. If I move it over to here, look, it makes, at this point it changes from negative to positive right here. Something's going on here. In fact, that's more important than these. I'll keep doing this story. If I keep going, look, negative, 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 still negative, still negative, still negative, still negative, still negative, still negative. Oh, but at some point around here, it becomes positive. I'm looking at this once again. And look what story this tells. If we just look at this function in general, we can see that this to here, concave up, which means the second derivative is positive. Same thing here. This is all concave up, which means the second derivative positive. But in the middle, this section is concave down, which means the second derivative is negative. So once you get more and more confident with these ideas, what we're doing, this whole number line thing I do in the middle of our practice questions, will become more and more interesting, or more and more, it'll make more and more sense. So we check the points in between where it's 0, and it'll tell us if it's concave up or down. So let me just show you how these questions are going to look. Now that I've blown away all your expectations, or put you to sleep, one or the other. So consider the graph below. M is a relative maximum. Little m is a relative minimum. From I to B, is it concave up or concave down? This is the first little piece of information you need to know. From I to B, is it concave up or down? Does it look like a positive smiley face, or does it look like a sad face? If it looks like a positive smiley face, it's concave up, because it looks like part of this curve. And in other words, that means the second derivative is less than 0, also known as negative. From A to I, let's see if I get any answers in the chat for this one. From A to I, what does it look like? Does it look like a smiley face or a sad face? Well, it looks like a sad face to me, or at least part of a sad face, which means it's concave down. And in other words, that means the second derivative is going to be, oops, the first one was positive, greater than 0. This one's less than 0. So I made a mistake there. This means second derivative positive. This means second derivative negative. Just trying to get these terms down in your head. I, what's going on at I? We have concave up, we have concave down. So it goes from a curve one way to a curve another way. It's like it gets twisted in the middle. Do you know what the name of that point is? If it gets twisted, it's called a changing point. There's one word for it. If you have the specific math term, it's called inflection point, where it changes from concave down, concave up. That's what it's called when you go from down to up. So I want to just show you something. It goes from this shape to this shape. It goes from concave down concave up. And this is our inflection. Okay, lots of information to take in. Honestly, the individual pieces of information are not that difficult, but I know that you might struggle with it for a little while because it's just probably new to you. But let me give you the big strokes, okay? There's only really 3 things going on here that you need to be aware of. But 3 things, key things. I'll just say intercepts. This is based off the function itself. You solve it for 0. You have your critical points, which is related to first derivative, or in other words, slope is 0. That is first derivative equal to 0. How do you think I solve for concavity? Which is right, that's like our inflection points and things. It's going to be our second derivative set to 0. These are our key ideas, our 3 things. If we combine all those things together, we can actually sketch the graph without ever having to use a calculator. You can always use your calculator to check it, but these are the big ideas. So now that we've got the big ideas out of the way, let's actually do some examples on it, and hopefully you won't be too scared by this. All right, determine the concavity and find any points of inflection of the function. Let's go one step further. I'm going to say, determine the critical points and the concavity, okay? Because we might as well, I want to give you the whole story here. So because I'm going to be finding x and y values, I'm going to set up my little table. We'll fill that in as we go. And let's follow our let's follow our steps one after another. So let's find our critical points. How do I get my critical points? Don't all yell at me at once. To get my critical points, I set the first derivative to 0. I need to get my first derivative. Now I'm going to set it to 0. I can factor out a 3 here, which gives this. And this is pretty easy to solve. Set that equal to 0. My first, wait a second. Ooh, that would have been too easy, wouldn't it? I missed a square. 3x squared minus 3. That was close. Now I factor out my 3. It gives me x squared minus 1. Remember, that's a difference of squares. Square root of the first one gives me x. Square root of the second one gives me 1. And it's plus and minus in the middle. What's my x values? I'm going to split it down here. I know x plus 1 equals 0. I can solve for that. So x equals negative 1. In this case, x plus 1 equals 0. Solve for that. That's x equals negative 1. These are my 2 critical points. I'll write them in my table. I'm sorry, I'm not paying close enough attention. This is a minus, a minus, there's a plus. Okay, I'll let you catch up. I got the first derivative. I set it equal to 0. Solved for my x values. That will give me the first 2 sets of critical points. They may be maximum or may be minimum. I don't know yet, but I'm going to put those back into my first function just to see what those points are. So I'm going to put negative 1 in. That's negative 1 cubed minus 3 times negative 1. That's a 2. So once again, I'm going to take these x values, put them in here, get a y value back. I get a 2. If I put a 1 in, it's a 1 cubed minus 3 times 1, so that's negative 2. So I've got my values in my table. I don't know if they're maximum or minimum yet, but I do know that they are either maximum or minimum. So what am I going to do? How do I test to see if they're maximum or minimum? What's the name of the test? Do you remember the name? It's called a something derivative test. It's very simple. If I want to test the first derivative stuff, I use the first derivative test, FDT. That means make a number line, put your critical points on it, and test to see what the sign of the first derivative is. So what I'm going to do, I'm going to put a 0 in to the first derivative. I'm going to put a 0 into this. I get 3, and then if I put a 0 in, this gives me a plus, this gives me a minus and a plus gives a minus. So in between -1 and 1, I get a minus. Let's check anything bigger than 1. Choose any number. What's a number bigger than 1? 2. So let's say 3, 2 plus 1, 2 minus 1. What does this give us? This gives us a positive. This gives us a positive. So the overall result is positive. It'll go here. Let's check anything less than 1. Let's try -2. So we have 3. I'll put in -2 plus 1. Try -2 minus 1. What are the signs here? This is a minus. This is a minus. Minus and minus give a plus if you multiply them. So it's a plus. I've done the heavy lifting for you. Can you tell me what I have here? At -1, is it a maximum or a minimum? So Abdullah's still alive. I'm not sure the rest. Oh, you are still alive. Okay. Yeah, it's a maximum. Goes from positive to negative slope. Boop. So that's a maximum for sure. I can write that everywhere I see it. I can say it's a maximum. Hey, it's a maximum. Hey, it's a maximum, guys. It's a maximum. I got it. I got it. I got it. What about the next point? It's going from a negative to a positive. That's definitely a minimum because it goes whoop, slope going down and comes back up. It's got to be a minimum, so I can label these wherever I see them, and then it's clear what they are. You can just label it somewhere just once, okay? Or you can finish the question and say, you have a maximum at -1 and 2, you have a minimum at 1 and -2. So that would be kind of our final answer for the critical values. Okay. That's our first derivative test done. We've done our critical points. The second derivative test is just as easy. In fact, it's almost always easier. And when we do that, that'll be kind of the end of the new stuff. So let's check our inflection points. The inflection points, I should say, when I went back here, concavity, I really should have written in this little point here. It's more of an inflection point we're looking for. And instead of being slope that it gives us concavity. That's a little bit more clear. So when I made that little cheat sheet earlier, maybe make a note that it was inflection points we're looking for, not concavity. In between the inflection points, we have concavity changing. So let's look at this. What do we need to do? The critical points were the first derivative. Inflection points are the second derivative. So we get the derivative of our get the second derivative of the first function. So just get the second derivative based off this. Y double prime. If y prime is 3x squared minus 3, what's y double prime? The derivative of this. So bring the 2 down, it becomes 6x. Right, 6x. That's our second derivative. In order to do this, the critical points were set at equal to 0. The inflection points will also be setting equal to 0. So 0 is 6x, or in other words, x equals 0. I'm just going to take that and test it again using what's called the second derivative test, which I also make a number line. Put the 0 on it, check left and right using this, and just tell me what the sign is. So if I put in, say, I don't know, -1, 6 times -1, what's my sign? Negative. So it's a negative. Anything bigger than 0, let's say 1. So 6 times 1, that gives me a positive. So the region after the 0 is a positive. And long story short, if it's second derivative we're talking about, what did I say about second derivative? I said if second derivative was negative or less than 0, it looks like this. So this region must look like this. And finally, the last thing, if the second derivative is greater than 0, which means it's positive, it looks like this, which means this region looks like this. Halas. Let me summarize. We have an inflection point at 0, 0. I know it's 0, 0 because if I put this x value back into the original function, it gives me a 0 and a 0 back. What else do I know? I know it's concave down anything below that 0, so x less than 0. I know it's concave up when x is greater than 0. Okay, these are my big ideas here. New questions, probably a little bit intimidating, but hopefully making some sort of sense to you. Is there anything I can go back through? I'll do another example. We have time, but anything I can clarify here? This will be a video you might want to review just in case you missed the pieces. But long story short, get the intercepts if you're asked for them, get the critical points in the same way, get the inflection points in the same way, and draw your number lines to make sense of everything. Let's see here. It says to sketch the graph. So I want to give you an idea of how to sketch this, okay? And we're going to want to remember our basics that I wrote before. So I'm going to just take this from earlier and use it, oops, to do the example. And I'll have some time to do just one example. And on Thursday, I'll probably use it as a review. But I want to get this done. I want to make sure you have what you need. So we need to sketch the graph. And we're going to sketch the graph by following the same steps that I've been following this whole time. I'm going to put everything together. So the first things first, I'm going to get the x-intercept. And how I do that, I'm going to set y equals 0. So take the original function, set it to 0. That means 0 equals 6x minus x squared. I'll move this over because I want to keep track of some things in the table here. So those are my table of values if I need it later. Let's solve this. Take out any common factors. So we have an x. This is a 6 minus an x. If we solve that, you should see we can set the x to 0. We can set the 6 minus x equals 0. This would be what x equals 0 is our first one. And 6 minus x equals 0, that means that we change the sign. 6. These are our x-intercepts. X-intercepts mean that y is equal to 0 at that point, so that's done. Okay, we can even put them on the graph already. Must be an x-intercept here, and there must be an x-intercept here. Okay, all we need to do now is go through the other tests and see what the shape is. So what's our next thing we need to look for? We need to look for our critical points, also known as our maximum and minimum values. To do that, we set the first derivative equal to 0. Remember, we're finding where the slope is 0. That'll give us a maximum or a minimum. So the critical points, get the derivative, first derivative, y prime equals 6 minus 2x. If you're not good with your derivatives, this will make you a problem. 0 equals 6 minus 2x. That means if I solve this, that means 2x equals 6. X must be 3. Can someone tell me if that's a maximum or a minimum? All I know right now is that this is a point where slope is 0 when x equals 3, of course, because if it makes this 0, it makes the slope 0, that's the x value that makes that 0. So is it a maximum or a minimum? Kind of hard to tell. Let's draw a number line. Put that point on it. Check our first derivative. First derivative to the left. So let's see, I'm looking at this. This is my first derivative. Sometimes I write it like this. So if I put anything below 3, what's the sign? Is it going to be positive or a negative? When I put a 0 in that, for example, it'll be 2, 3 minus 0. That's all a positive. So the slope is positive in that region. It's going to look like this. I can pretty much guess it's going to be minus over here, but I'm not sure. So let me put in anything bigger than 3. I'm just going to put in a 10 for fun. So 2, 3 minus 10. That gives me a negative. So the region is negative like I expected, which means it'll look like this. So long story short, it means that I'm going to have a maximum value when x is 3. So it's a maximum. So when x is 3, I'll put it in my table. We have a maximum. What's the y value when x equals 3? Just to go back and check it, put a 3 in here. So 6 times 3 minus 3 squared gives me a 9. And I have everything I need, almost. I should also check the inflection just in case. Even though I know that there's a point at 3, 9, which is here, I haven't actually checked my second derivative. So let's check our second derivative down here. Inflection, also known as concavity. Check the second derivative, set it to 0. Well, the second derivative, y double prime, is actually just negative 2. So you don't need to check it. We can just say y double prime is less than 0 because it's negative. So it's concave down always. It's going to look like this, which is no surprise because it only has that maximum. We can sketch it now. It looks like this. I want to make one note. On the left side of this, positive slope. On the right side of this, negative slope, which is why I was able to graph it using that number line. There's one more just quick practice I'm going to go through. I'll go through it again on Thursday, but just so I have an idea. Actually, I'll leave it here. I'll do the practice on Thursday. Is there anything that I can clarify, or are we good for now? There's a couple practice I'll do Thursday. It's a worksheet and some more examples. But how do we feel about this on a scale of 1 to 10? This is the whole unit. We've done everything now. You feel fine? It means that you are handling Unit 6 okay. I'll show you just what to expect. We won't actually complete every single thing, but just if you look at my prep notes, there is, and I've got a reference video here, the only thing extra that I would do is sometimes the inflection doesn't work out to a single value, so we need to combine the number lines and make a little bit more tricky graphs. I'm not sure I'll go that deep into it because I want you to know the basics. So the difficulty will stay about this example. And so if you feel okay with that example, you're doing great. All right. So just to give you, I'll stop the recording. Thanks, everybody.